Sea waves are the most powerful energy carriers in renewable energy sources, as they show large energy resources in all geographical areas. Scientists believe that the waves in the ocean are capable of generating 2 terawatt per year all over the world. Global theoretical energy from waves corresponds to 8 million terawatt hours per year, which is about 100 times the total hydroelectric generation of the whole planet. To produce this energy using fossil fuels, it would produce 2 million tons of carbon dioxide emissions. The fossil fuels contribute to about 80% of the gross primary energy, and the International Energy Agency anticipates the same in 2030, considering an increase in global energy consumption by 1.6% per year. Obeying the rules of the Kyoto Protocol, wave energy can contribute towards the diminution of air pollution. Therefore, it is highly suggested to exploit this technology towards its fullest extent. It has been found that the world has an 800,000 kilometer of coastline, exceeding a wave power density of 30 kilowatt per meter. In 1924, the first study of large-scale tidal waves started in various islands using electric stations, ship locks, and powerhouses. The ways of development of wave energy conventions have been going on for many years. The developed devices have different models and sizes. This often leads to expensive and costly processes for large and sophisticated devices. However, the cost related to construction, repair work, setting up of electric cables, grain storage facilities, scale machines, equipment and project management does not depend upon the size of the wave energy converter or WEC. Therefore, larger devices that generate large amounts of energy are better than smaller devices. There are only few WECs which are capable of improving their energy generation, compared to wind energy where we can increase energy output by increasing swept area. This is because, from the beginning of their development, WECs have optimum size and hence the freedom for further product development is difficult. The wave motion, as you know, is very arbitrary. Hence, there needs to be a mechanism that would utilize and convert the unsteady input to a constant and steady output in the form of electricity. The forces from the waves are observed through an absorber, possibly a buoy. This absorbed energy can be directly converted into electricity using a linear permanent magnet generator or in several stages using hydraulic and mechanical transducers. These converters are to be selected keeping in mind the factors such as life, durability, reliability, efficiency, and many more. The generator system of the WEC is a topic of ongoing research to possibly increase the efficiency of the whole system. Another important factor to be considered while designing a WEC is its location of implementation, as the requirements and constraints have to be satisfied. Since wave energy is relatively new, there are fewer areas that currently have or are installing wave farms. Some main areas for wave farms are Portugal, the United Kingdom, Australia, and the United States. There are also possibilities in Russia and Italy for potential wave farms.
We live on a water planet. Roughly 71% of the Earth is covered by water, and it's constantly in motion. Tides surging rhythmically, powerful currents coursing beneath the surface, waves rolling across oceans and crashing against coastlines. The water of the oceans is almost always in motion, hardly ever interrupted. All that motion produces mind-boggling quantities of kinetic energy. The total wave energy resource is the same order of magnitude as world electricity consumption, approximately 2 terawatt. Many companies are developing technologies to convert this inexhaustible energy into electric power without the emission of harmful greenhouse gases. One of the solutions is wave power station, Working principle of wave power station is pretty simple. Enclosed chamber has an opening beneath sea level, which allows water to flow from the sea to the chamber and back. Water level in the chamber rises and falls with the rhythm of the waves. The wave action alternately compresses and decompresses the trapped air, forcing an airflow moving back and forth through a Wells turbine that drives a generator and produces electricity. Main feature of Wells turbine is that the turbine is driven in the same direction by both forward and reverse airflow through the turbine. Even relatively low wave motions can generate enough airflow to keep the turbine moving and to generate energy. As we have already said, the most commonly used air turbine for this application is the Wells turbine. As we also already know, the air is forced forwards and backwards through the turbine and causes the rotation of the turbine. This generates mechanical energy that is converted into electricity by a generator. The Wells turbine has a special feature. It always rotates in the same direction, regardless of which direction the airflow comes from. How is this possible? This is possible because of the symmetrical shape of the rotor blades. As the air hits the rotor blade, most of the flow is deflected in one direction and pushes the blade in the opposite direction. Due to the symmetrical shape of the rotor blades, the same effect happens when the airflow comes from the other direction. Therefore, this Wells turbine always rotates in one direction, regardless of the airflow direction, and guarantees the continuous rotation of the turbine. Important to remember, Wells turbine always rotates in the same direction. Wells turbine also have installed flow controller, with which we regulate airflow through turbine. The Wells turbine must be turned on initially. The airflow alone does not get it to rotate. This turbine is one of the simplest and probably the most economical turbines for wave energy conversion. It does not require rectifying air valves and can extract power at low airflow rate, when other turbines would be inefficient. It has very few moving parts. None of them are in the water, needs no gearboxes, is easy to maintain and achieves an efficiency between 40 and 70%. In this way, we can generate energy with a wave power station, day and night, all year round, as long as there are waves. The world's first 75 kilowatt test wave power station of this kind was put into service as early as November 2000 on the Scottish island of Islay. The commissioning and maintenance of wave power station can be carried out entirely on land, without incurring costs for the use of marine infrastructures or boats. The shorter grid connection to this system is simple and inexpensive, and its environmental impact is minimal or none.
Advantages of wave energy are renewable. The best thing about wave energy is that will never run out. Unlike fossil fuels, which are running out, the waves flow back from the shore, but they always return. Environment friendly. Also, unlike fossil fuels, creating power from waves creates no harmful byproducts such as gas, waste, and pollution. Not expensive to operate and maintain. Disadvantages of wave energy are suitable to certain locations. The biggest disadvantage to getting energy from the wave is location. Only power plants in towns near the ocean will benefit directly from it. Effect on marine ecosystem. As clean as wave energy is, it still creates hazards for some of the animals near it. Depends on waves. Sometimes you'll get lots of energy, sometimes almost nothing. It needs a suitable site where waves are consistently strong.
Here are some environmental and health and safety, social and ethical consideration of ocean wave energy. biofouling, commercial and recreational fishing, the installation of decommissioning of equipment, conflict with other sea users, visual appearance and noise, reduction in wave height from wave energy converters. Marine habitat could be impacted negatively or positively. Toxic releases related to leaks or accidental spills. Example problem of wave energy. So based on the figure below, suppose crest to throw height of a wave is h, wavelength is lambda, wave period is t, and the wave shape follows the sine function. So given surface wavelength lambda equals gt squared over 2 pi and area above mean level, a volume per unit thickness is equals to h over pi times lambda over 2. So in this diagram, here is the solution. Mass of a crest or throw per unit length. So we get the mass m equals throw times the integral from 0 to lambda over 2 of h over 2 sine 2 pi over lambda x dx is equals to rho lambda h over 2 pi. So next, we want to know the energy stored in a wavelength. The total energy of a crest is not the potential energy from the crest to sea level, but it's the potential energy from a crest to a throw. So we need the energy to raise the water from the throw below sea level to the crest above sea level. So energy stored in a crest per unit length. So delta E is equals to mg delta h, so equals rho lambda h over 2 pi g times pi h over 8 is equals to rho lambda gh squared over 16. So the energy stored in a full wavelength is equals to 2 delta E equals rho lambda gh squared over 8. So this is the energy gain per unit length for a whole wavelength. As a wavelength corresponds to a wave period, the wave power per unit is P equals 2 delta E over T equals rho lambda gh squared over 8 all over T. So equals rho g squared th squared over 16 pi. So in this calculation, we only calculate the energy stored in the wave. So the wave is not doing work to the other media. The total amount of energy in the wave remains the same. Once we calculate the total energy in a wavelength, we don't have to relate the process to a half wave period or a quarter wavelength. So with this formula, with rho equals 1g over centimeter cube and g equals 9.m over s and pi equals 3.14. So by substituting, P is equals to 1.91 kilowatts T of S H of M squared per SM cube.